Today we are going to take a look at section 2.2. It's titled Describing Sets. And we are going to encounter a lot of notation today. Some of it is probably things you've seen before and familiar, and some of it probably isn't. So this front page that you're going to be writing on your notes, a lot of notation. To start with, a couple of words that you're familiar with. Maybe they have this sort of definition for you all the time, and maybe they don't. A set is any collection of objects. So a set can be music files in your phone that you have downloaded to your phone. A set could be the people in your family. A set could be your friends on Facebook or wherever you've got your friends. So it can be objects, but it could actually be like people too, all right? Elements are the individual things, whatever they are, in your set. They're the music files, or they're the people, or they're the songs, or they're the whatever they are that you're describing. There are two ways to describe sets that we're going to focus on. And we're going to focus, obviously, mostly on mathematical sets, although we will talk about some other ones too. One of them is a listing or a roster method. So the word listing or the word roster are interchangeable. And literally what it looks like is simply a list of things. So if you were to talk about the people in your family, like maybe your immediate family, right? It would be a list of all of their names, okay? If you were to talk about, and I'll give you an example of a set of numbers, and we were talking about this set of numbers. This is an example. Even if I can't list them all out, if I put the ... this would be considered a listing or a roster method. Okay, so these are whole numbers, or they're counting numbers, they're natural numbers, they're, any of those descriptions. You can even say they're integers. We're going to talk about all those different things in a minute. But they're 7 and up, right? They don't include all of them, like 6 is not in this list. But they're set from 7 and up. There are times when it's more convenient to actually describe something in a more concise way using a little bit of symbols. Now, this feels a little bit weird, so just write it down with me, and then I'll describe how we think about this. So you start again with a curly brace. And I'm going to just do the same set, but this is the set builder notation. You're going to use a variable name, x, or whatever you like. And a vertical bar. And then you're going to use an inequality notation. So on this one, x is greater than or equal to 7. Okay, so that tells you sort of where you start in the list. But it also needs to tell you what kind of numbers this does and doesn't include. For example, this doesn't include fractions and decimals, right? It's not doing that kind of number. So I need to tell it that it's a natural number. So again, write the symbols down and then I'll explain what they mean. There's an x. This looks like a curly E, and it is curly. Like it's not boxy. Do not use the boxy E. The boxy E in your calculator means something different. All right? It looks like there is a curve to that E. And then you're going to put an N that has 2 lines on the left. And then close your brace. Just write it down for a second. Okay, I promise I'm going to come back to this, but it'll make more sense to come back to this after I've given you all of the sort of big list of symbols that you're going to need and want. So come with me to the next, I'll go to my next slide, and you're going to go to your next set of things that says symbols used in set builder notation. So the first symbol I'm going to talk about is that curly E. That curly E means is an element of. Okay? Element. We saw that symbol or that word on a previous slide, right? Element. Element means that it's among those things that you're talking about. It's the people, one of the people that are in your family. It's one of those names that's in your Facebook contact list. It's one of those files of music that's on your phone. Whatever your collection of objects is, it's one of them. Okay? So over here, this E means that X, whatever it is among, it's one of the elements of the things that came next. So what are those things that came next? Well, the one that I just gave you was this N with the 2 lines on the left. If this is printed in a book, there doesn't look like there's 2 lines. It looks like a really bold line on the left. That's how it'll print when it's printed. When we write it down, it's a lot easier to do a double line than to make something look truly bold. That's harder to do when we write. So we do a double line. This actually stands for the natural numbers. So natural numbers are the numbers you naturally learn to count with. So when you start learning to count, what number do you start with? 1. And you go to 1.5 next, right? No. You go 1, 2, 3, and so forth. These are called the natural numbers, otherwise known as the counting numbers, more affectionately, right? They're the counting numbers. So anytime you see this N, it means we've got the natural, the counting numbers. So over here, this is telling you that the values in this set are the counting numbers. Okay, 7, 8, 9, 10. We're not getting 7.5 in my list. All right, there's no 7.999. None of that's going on, right? So over here, let me finish telling you then, because I'll finish my list, what this actually says then. This is read as, this is all X. That vertical bar is read as the word such that. You know how to read the next one. It's X is greater than or equal to 7, right? And the last part is, and X is a natural number. The one thing that you could do that would be perfectly acceptable is you could switch the order here. I could put X as a natural number first and X is greater than or equal to 7 second. That would be fine. So there's really not an order to that. But that describes the previous set. These are natural numbers, and they're numbers that are bigger than 7. Okay? So that's called set builder notation. Some other symbols that you will see used throughout our time together. We got natural numbers. That's the N with the 2 lines on the left. You've got a Z with 2 lines in the middle. Z references the, I feel like I left one. Well, I did leave one out, but it's left out of my notes too. I'll put Z first. These are the integers. So your integers are positive and negative whole numbers. So you have ... -3, -2, -1, 0, 1, 2, 3, and so on. These are your integers. We will encounter these guys in chapter 5 of our book. The one I skipped accidentally, my apologies, is a W with 2 lines on the left. I don't know why it's not in my notes. It should be there. Any idea what those might be? Yeah, these are the whole numbers. So the whole numbers are the same as counting numbers, but they include 0. You might be thinking, okay, well, I get N natural, W whole, Y is Z for integers. It has to do with the Latin word for integers. My apologies, I don't know what it is, but that's where it's coming from. The other issue is that to use I for integers would be a problem because I is sometimes used for irrational numbers, I for irrational. There's another one that doesn't match sort of its letter at the beginning. It's a Q. Q stands for rational numbers. Rational numbers are any numbers that can be written as a ratio or fraction. So fractions are also called ratios. For those of you who've taken proportional and statistical reasoning, that's what happens in chapter 6 in our book. So that's where the word rational comes from. Any idea why Q might be used for rational numbers? It's not from Latin, by the way. Say that again.
Quotient?
The word quotient. Yeah, quotient means division, right? And fractions, it's exactly what's going on with a fraction, right? It's a number divided by another number in a ratio form, right? So quotient is where the Q comes from. It's from quotient. And that actually leaves us the R for real numbers. And so real numbers will include all of the things above. Those are all real numbers. But it also includes things like square roots, looks like square root of 2, pi. You encounter that in geometry, right? Very early, this is middle school age, right? 7th grade or so. So you encounter pi. So those are irrational numbers, but they're still real numbers. And the difference between those numbers like square root of 2 and pi is that they cannot be written in an integer divided by an integer form. And you might think, wait a minute, but one of those versions for pi is that you can write it as 22/7, and that's an approximation for pi, but it's not exactly pi. So that's the difference there, is that it can't be written actually in a closed division form like that. One other symbol, back up here kind of with the element, is that if you write an element symbol and draw a line through it, what do you think that means? Yeah, is not an element of. So if I were to talk about Aspen, I would say she is not an element of my family, right? She's not one of my family members. So that would be is not an element of symbol. All right, so we're going to do an example, much like this previous one here, where we're going to talk numbers for the moment. And we're going to take both the listing or roster method and the set builder method, and we're going to write the set of natural numbers less than 5. So if we were to write out in a list the set of natural numbers less than 5, make sure they're in curly braces, but what would I write down in my list? Yeah, 1, 2, 3, 4. I don't include 0 because 0 is a whole number, but it's not a natural number, okay? Not considered natural numbers. This is just a list 1 through 4. Set builder notation, which you're a little bit less familiar with, still has the curly braces. The beginning part of set builder notation always looks the same. It's this sort of generic form that says, I'm going to talk about a letter X, a number X really, and it's everything that follows after that. So these are all the values that fit my criteria, and then I write down what the criteria would be. So what would the criteria be with this description? Less than 5. And then what else? X is an element of the natural numbers. And again, those two quantifying statements there could be in either order. So I could start with the X is an element of the natural numbers, and the X is less than 5 seconds. That would be okay. All right. A couple of vocabulary things that make things a little bit awkward. Usually when we talk about vocabulary, equal and equivalent mean the same thing. Right? Equal and equivalent, we don't think about the meaning different. They do mean something different for set notation. Equal sets are sets that contain exactly the same elements. So if my husband and I were to each talk about our immediate family, those would be equal sets because we're talking about the exact same group of people. Exact same group of people. I'm going to skip over one-to-one correspondence for a moment and jump down to equivalent. I know it's on another page for you. I'm sorry about how that works out on your notes. But equivalent means that they have the same number of elements. Okay? So I have 8 people in my family. Does anybody else in the immediate family have 8 people in this class? This was a lot easier than when I had 6. You do?
Yeah.
Fantastic. Colton and I each have 8 people in our family. So when I talk about my family and when Colton talks about his family, those would be equivalent sets because there's 8 people in each of those groups, okay? And what does that mean in terms of the definition that I sort of skipped over? Well, one-to-one correspondence means that I could set them up in pairs, right? Like when you come into class and I put you in group work pairs, I could set them up in equal pairs and there'd be nobody left over. Okay, so Colton and I could sit down and we could line up all the list of people. We could put them in one-to-one pairs or one-to-one correspondences, and there'd be nobody left over. And that's what it means for sets to be equivalent. They have the same number. They can be put in one-to-one correspondence. Make sense? Okay. So you might ask then, if I were doing this with my family the last time that I did these notes, this worked because I had 6 people and now I have 8, so that doesn't work very well. But you might ask, well, how many different one-to-one correspondences could you set up? Like, how do you know how many different ways you could make those pairings? So the way that it works is, let's actually imagine 6 men and 6 women in the room, and they're all going to go on a blind date. No one is attached, okay? There's no couples to start with. Okay, so there's 6 females in the room. We're not going to do it that way. There's 6 males in the room, all right? And the females are waiting out in the hallway. Okay, and young lady number 1 comes in and she gets her pick. How many choices does she have? 6. Once she makes her pick, though, and person number 2 comes in, how many choices does person number 2 have? 5. And once that pick has been made and person number 3 comes in, how many choices does person number 3 have? 4. And we can see how that process continues, right? There's always one less than there were before because once a pairing has been made, I have fewer choices to pick from. So a visual way to do that, I always draw it with lines, is that I have 6 choices to make. So I have 6 lines that I draw. The first line that I draw has 6 different possible outcomes that could go there. The second one is that second person coming in and saying, how many choices do I have left? And they have 5 choices left. And then I have 4 choices, 3, 2, and 1. And when I multiply those together, that will be the total number of distinctly different, at least they differ by 1 correspondence, right? Combinations that could be made. And so what is 6 times 5 down to 1? Somebody have a calculator for us? It is 720. And again, if you've taken proportional and statistical reasoning, you've seen this process before. Do you remember what it's called when you multiply 6 times 5 all the way down? No. It's called a factorial. It can actually be represented with an exclamation point. Exclamation point means factorial, and it means times all the way down, multiplication all the way down to 1. For the whole numbers all the way down to 1. We won't use that notation. I'm just sort of drawing it in. If you've seen it before, it doesn't mean it's excited. I mean, it is. It's worth 720 now, right? Not 6, but yeah, it means multiplication down to the value of 1. All right. A little bit more notation because we don't have enough, right? More vocabulary. Cardinal number. Cardinal number simply means the number of elements in the set S. And it's written as N parenthesis S close parenthesis. N meaning number. So if I were to talk about my family, right, and I say the number in the hands, we'll say household, and we'll be very clear, people, otherwise my children will start throwing in the animals. Do you guys do that? Do you count them? Yeah, I have 2 children at least that count them. This would be 8. The number in my hands, people, is 8. Finite set means that it's a set for which the cardinal number is a whole number. Okay? It means the same thing you mean when you say a finite value. It has a specific number. Infinite would mean infinite, right? I mean, like you want to define it almost with itself, right? Infinite means that it does not have a counting number as a cardinal number. Does not have a cardinal number that's a counting number, a whole number. And then the empty or null set is the set that contains no elements, has a cardinality of 0. And there's several ways that you can write that. One of the ways that you can write that is a 0 with a slash through it. That stands for the null set. So those of you who maybe already write your zeros with slashes through it, please don't do that. It has another meaning for us. It means the null set. Another way that this can be written is, I like this one actually, curly braces with nothing inside. It's just so descriptive, right? There's braces there and there's nothing in it. This is the null set. So I'm going to write now something that you cannot write, and we're going to put big old like slash marks through it after I write it, and you're going to too. You cannot do this. Don't do that. Put all kinds of marks through that so you remind yourself, do not do that. Okay? That actually would mean you have a set with the empty set inside of it, which means there's something in it. I mean, there's something in it that is the set with nothing in it, but it's just, don't double up the notation. It's one or the other. It's not both. Okay? Now, I want to make one comment about the way that this is describing it. It's a set that has a cardinality of 0 business here. What that's actually saying is that if I try to do the cardinality of the empty set, right, number of items in the empty set, that equals 0. That doesn't equal the empty set. Okay, cardinality means the number of something. Well, the number in it is 0. So you might feel like, why are we talking about sets that have nothing in them? Well, because they exist, right? If I were to be talking about how amazing and beautiful and wonderful all the babies are that live in my home, they're fantastic. They sleep through the night. They change their own diapers. They're fantastic. I mean, like, I can say that and you can't even tell me that I'm lying because, right, it's that hypothesis conclusion thing we did before with the implications, right? There are no babies living in my house. I have no babies right now. I mean, all my children are sort of my babies, but you know what I mean, right? There are no infants in my home. So we can talk about that, and it sounds kind of funny, but that would be a null set for my life. You're going to do a null set for me next time when we come to class. So we're going to find a few cardinalities next, okay? So cardinal numbers, again, means how many items are in the set. So go ahead, if you will, and let's call these sets A, B, C, and D. Sets are always capital letters, so that's why I just did that. And notationally, we are finding the number of items in set A. So I've got all these numbers. They start with 9, 10, 11, continue on till I get to 99. How many numbers are there? How many? 91. So where did you get 91? Okay, good. So that's exactly right. In fact, I'm going to write it over there. Why is it minus 8 and not minus 9, Michaela? Yeah. So I need to only not count the stuff that came before 9, right? The 9 is in my set, so I don't want to subtract that 9 out accidentally. So I subtract 8 because those are the things that came before, the 8 items that came before the 9. Okay, so this is the number of items in set A. How about the number of items in set B?
2,000 minus 2, and then, which has a 2, minus 2, and then divide by 2.
You're so close. Is anybody telling what's off? This is what he suggested.
Yeah.
What's off? Minus what?
Minus 1.
Close. It's actually minus 0. So where's the 0 coming from? Yeah, it has to be the number that comes before, which is why I know you guys want to say the number 1. But the number 1 is not in this pattern of numbers, right? What's the number that comes before in the pattern that I have? It's actually 0. So it would be minus 0. I know that isn't very exciting to subtract, but it would be the number that comes before the 2 in the pattern that I have. And then why are we dividing by 2? Yeah, because it counts by 2s, right? It's all evens or it's skip counting, however your description is. So what is 2002 minus 0 divided by 2? 1001. Okay, C and D are different just simply because they're in set builder notation, and so we have to think a little bit differently about them. So let's read what we have. Set C says that I have all x squareds, and it tells you that the x values are 1, 3, 5, all the way up to 99. So it might be helpful to start by listing out what you actually have. What items are in this set? Close. 1 squared. Yeah, 3 squared. 5 squared. All the way up to 99 squared. So let me first ask you. This one and this one, this set of numbers, are they equal? Equal means exactly the same. No. Are they equivalent? Yes. Equivalent means I can put them in one-to-one correspondence. Right? The number 1 corresponds to 1 squared, 3 to 3 squared, 5 to 5 squared, 9 to 9 to 99 squared. They're in one-to-one correspondence. Why does it matter? Well, the reason it matters is because it doesn't matter if I talk about the set that's 1 squared, 3 squared, 5 squared, 99 squared, or if I talk about the set that's 1, 3, 5, 9, 99 all the way up. There's the same number of things, right? They're the same number of them. So I just need to know how many things, how many elements are there here. So how many elements are there here? How many items are there from 1 up to 99? One of two things is going on. Either I've stumped you, or some of you are saying, this is so obvious I don't want to say anything out loud because what if I'm wrong? So what kinds of numbers are these? They're odd. Good. The last question that was even, y'all did not have a trouble. But all because then, now that it's odd, you're like, oh, I don't know what to do, it's odd.
Would we do
Close.
Would it be 50?
It's 50.
Okay.
You did 99 minus -1 divided by 2.
You can definitely do that, Hannah. Yeah. So for some reason, odd numbers feel more awkward to us. They do. That's just a true statement. At least I think that's how we feel about it. We can still do the same thing we did on the last problem, which is to take the final number, 99, and subtract the number that would come before it in the sequence, also feeling a little bit awkward and odd because it's negative, right? It's the number that comes 2 before 1, which would be -1. If we do that and think about it that way, that's okay. I get 100 divided by 2, and that's my 50. You could also simply think, if I had all the numbers between 0 and 100, that'd be 100 numbers, right? But I don't have all of them. I have only the odd ones, and that's half of them. It's another way to think about it. And I'm sure there's some others. Those are the two ways that I usually start to talk through it. Colton?
So with the squared numbers, is it supposed to just show it's like what it's doing?
Yeah,
Or would
it's
it
supposed to
line up
show...
like 50 and then the squared side?
No, the squared actually tells you what items are there, but it doesn't affect how many of them there are.
Oh, okay.
So yeah, the items themselves are not 1, 3, 5, 7, 9. They're actually 1, 9, 25, 49, 64. I mean, those are the numbers that I actually have. but they're in one-to-one correspondence with the previous number 1 through 99 they already had. So yeah. All right, last one of these. This is an interesting one. This one says all x such that x is equal to x plus 1. So again, it might be helpful to very first describe what numbers this is referring to. So what do you think might be in this set? Okay, let's check 2. Does 2, oops, I mean right there. Does 2 equal 2 plus 1? Nope, that doesn't work. So this doesn't work. What's that? Odd numbers, so let's try an odd number. Let's just try one. How about we try 3? Does 3 equal 3 plus 1? Nope. Negative 1. Negative 1. Does negative 1 equal negative 1 plus 1? It's empty. You're exactly right. This is an empty set. There's nothing in there that works. Right?
That would make sense. Because even if you did 0, it's still 0.
Yeah. You can never have the same thing if you add one more to it, right? That's what this is saying. I need something that when I add one more to it, it doesn't change. That doesn't work. That doesn't work. So this is the empty set. So the number of items in set D is what? 0. There's nothing in this. No number will work. No number will work.
Can we write it like that, or do you want us to put like the empty brackets?
Well, if you want to put the empty brackets, it would have to look like this. The answer is still 0. All right? Now, set D is equal to the empty set, but that's not the question that was asked. The question we asked was, what's the cardinality? Cardinality is a finite number associated with what we were describing. All right. We are going to do 3 more definitions, and we'll stop for today. Whoops, I guess this slide did not get cleared off. Let me try that. Okay, Venn diagrams. Venn diagrams are diagrams used to illustrate ideas in logic. They will have a rectangle. That's what I just erased. The rectangle represents the universal set U that contains all elements being considered in the discussion. If we are given a set F, then the complement of F would be all elements that are not in F. For example, let's say that U is all OBU students. All of our OBU students. And since I used F, we're going to say F are our female. Whoops. OBU students. So inside of our rectangle, we would draw a circle. The circle would be set F, which would be the female students. And F with a line on top would be the complement of female students. So if you're talking about all OBU students and F is the female students, what would the complement of F be? Your male students, right? Still male OBU students. We're not all of a sudden, dragging in Joe off the street, right? Still talking about OBU students because it still has to be in the universal set, but it's the males in the outside. So visually speaking, this right here, set F, would be our female students. And then the outside of F, still in the rectangle, but the outside of F, you like how I use pink and blue? Yeah, that's good, right? This would be F complement, the way that I've done it. And it would be the male students. A couple other things just so that you're aware. I said F is written with the bar on the top, and it is, but if you see this in other literature, there's two other common notations for complements, and you should be aware of them because Venn diagrams in my life have shown up as early as 2nd grade for my children. Okay, they use them a little differently than I'm showing you the uses of them, but they use them even in 2nd grade. So even those of you who are like, I'm going to teach the little ones, you still may encounter these. Sometimes they put a hash mark like that at the end, like an accent mark for complement. And sometimes they put a little C, kind of like as a superscript, for complement. Those are two other notations that are sometimes used. Your book uses the bar on top. And that's where we're going to stop for today.